In SAC 329, problem number 1, we want to substitute this expression for y over here and this expression for v into this equation and prove or show that it leads to an identity. In this differential equation, we never have y by itself, so we're going to take the second derivative of y with respect to x, substitute it in here, and take the second derivative of y with respect to t, and substitute that into here. And then the v goes in there as well. So let's get started by taking the second derivative of y with respect to x. I'll copy down the y first. Okay, and this means second derivative is curly d's, mean keep everything else constant. In particular, in this case, keep t constant while you take the derivative with respect to x. dy by dx, I can emphasize that I'm holding t constant by means of a bar, a vertical bar with subscript t. And okay, I got a constant out front. And then times the cosine of an argument. So I'll take the derivative of that. That's minus the sine of the same argument. Times the derivative of the argument with respect to x, which will just be the 2 pi over lambda. And let's see if we can go ahead and take the second derivative right there. d squared by dx squared. Simplify later. Also, holding t constant here. Constant out front remains the same. I'll leave that minus sign there. So it's a minus 1 constant. And then the sign of an argument gives the cosine. Derivative of the sine with respect to its argument is the cosine of the argument. And then times the derivative of the argument with respect to x in this case. I get a 2 pi over lambda. And then times this constant that was out back, which is the 2 pi over lambda, which was already there. What I've used is the chain rule for the function of a function. I used it twice. So took the derivative of the cosine with respect to its argument, gave me minus the sine of the argument, and then times the derivative of the argument with respect to the variable, with respect to which we're taking the derivative overall. Let's go ahead and simplify this a little bit. Rolling the t constant is, I'm going to call it 2 pi squared is the way I write that, divided by lambda squared. There's a minus sign that goes out front. Now I've taken care of all that and that. I get the y max times the cosine of 2 pi over lambda times x minus 2 pi over capital T, the period, times the lowercase t, the time variable. Alright, then the other thing I need is the derivative with respect to t, the second derivative with respect to t. I'll go ahead and grab a copy of this. Put it down here. Alright, this is what I'm taking the derivative of once again. So now I got to take the derivative with respect to time. dy by dt is going to be equal to, okay, I got that constant out front. This is holding x constant. This is supposed to be just a vertical bar here. I got the constant out front, y max. Okay, now I want to take and multiply the derivative of the cosine with respect to its argument, which will be minus the sine of the argument. And then times the derivative of the argument with respect to t this time, because we're taking the derivative with respect to t. So it'll be times a minus 2 pi over capital T. This is, you can think of that as taking the exponent here, which is a 1, that's an implied t to the 1, bringing it out front, and then reducing it by 1, which gives t to the 0, which is just 1, and I didn't write the 1. Or you might remember that the derivative of t with respect to t is just 1 itself. And the derivative of a constant times t with respect to t is then just going to be that constant. Alright, let's take the second derivative before we clean things up even. You could clean things up first, simplify, that is to say. This is holding x constant, but I prefer to just keep on going here with taking derivatives. So I get the constant out front times another constant, the minus 1, and then times the derivative of the sign with respect to its argument, which will just be the cosine of the argument. The argument is, of course, whatever you're taking the sine or cosine of. Minus 2 pi over capital T times lowercase t completes the argument, and then times the derivative of the argument with respect to the time, and that's a minus 2 pi over t, and then times this constant, which was in the expression I'm taking the derivative of. And now I'll go ahead and simplify that a little bit. D squared y by dt squared, holding x constant, is, I do have 3 minus signs, so that's an odd number, so I have a negative. I'll put the 2 pi over t times 2 pi over t, I'm going to put it in this form. 2 pi squared over t squared times the y max times the cosine of its argument. And I think we're ready to substitute stuff in. So we got this expression is going to go in. This expression, and this expression goes in for v. So first I need the d squared y by dx squared. That was this one. So I'm just going to grab it. So try putting that down there. And then we can say equals, and really it's a question mark there. We want to see if it does lead to an identity. And then we got the 1 over v squared, which is going to be 1 over lambda over t all squared, or it's the reciprocal of this expression squared, so t squared over lambda squared. T squared over lambda squared. And then I just need this expression. I think it might be faster to grab it. Alright, times that. I do need to put it in parentheses. So we'll go ahead and put some parentheses on here. Right there. Maybe get rid of some of these red lines. Alright, so this is our expression. I'm going to go ahead and cancel out the T's, the capital T's. And then just compare. I got minus 2 pi all squared over lambda squared. There's minus 2 pi all squared over lambda squared. Y max, there's a Y max here. And the cosine of this argument, here's the cosine of the same argument. So I have the exact same expression on both sides, hence this is an identity. And hence, this expression with this expression for v really is a solution to this equation. So we proved it by substituting in the two expressions and evaluating and showing that it leads to an identity. No more question mark about those being equal. And that wraps it up for SAC 329, problem number 1.